Yeah, well, I'd like to begin this talk by explaining what a B-manifold is. I understood Eva talked a little bit about this last week, but since a lot of you who were here today were not here last week, I think I owe it to you to explain the notion, at least. So the notion of B-manifold involves a notion of what are called B vector fields. And what B vector fields are explained on this slide. The ingredients you need is an n-dimensional manifold, cap M here, and sitting inside it, a codimension 1 submanifold. And when you have that data, you can define a very interesting sheaf. It's called the sheaf of B vector fields, and it's defined as follows. If you take any open set in M and take a vector field on that open set, you decree that it's a B vector field if for every point on the intersection of that open set with Z, the vector field at that point is tangent to Z. This is the notion. And the sheaf that you define this way is a sheaf of modules with respect to the sheaf of C-infinity functions on the manifold. So let me now state a very important property of this sheaf of B vector fields. So the property is this, that the sheaf is a locally free sheaf of C-infinity modules. And that's very easy to see just by staring at these vector fields. And it has an important corollary. And the corollary is this, that there exists a vector bundle on M having the property that this sheaf is just the sheaf of sections of this vector bundle. It's a very nice fact. It's a special case of a very general fact. Whenever you have a locally free sheaf of C-infinity modules, you automatically get a vector bundle attached to that sheaf. It's a very interesting way to get to construct interesting vector bundles on a manifold is to exploit this. But at any rate, I'm exploiting this result here, and hence I'm getting from this sheaf of vector fields a vector bundle. Also, another important property of this sheaf is that if you have two B vector fields, then you take their Lie bracket, you again get a B vector field. So these B vector fields are closed under Lie bracket. Well, what that enables you to do is to define a Delzant complex associated with this sheaf. And the way that you do that is as follows. It's a familiar formula that I think all of you have seen. So you can associate a Delzant theory to the sheaf of vector fields by the following, in the following way. So you have this vector bundle, and so you can take its vector bundle dual, and you can take the exterior power of this vector bundle dual, and then you can define a class of sort of generalized Delzant forms just to be the global sections of this vector bundle. So you've now created a sort of a class of what you might call B-Delzant forms. And using this property that I pointed out here, this bracketing property, you can now define a Delzant D operator. You just take the standard recipe, you've all seen this recipe for how to define the Delzant D operator in terms of vector fields. And it makes perfectly good sense in this more general sense, because in this standard formula for the Delzant D operator, you now can make perfectly good sense of this bracket operation on the second line here. So this then gives you a Delzant D operator on this space of B Delzant forms, and it's very easy to check that this Delzant D operator is a D operator. In other words, that the square of this operator is 0, and so then that means that you now have a B Delzant complex. And it's easy to see that if you restrict this to the complement of Z, you just get the ordinary de Rham complex. But it's a very nice general fact that in many cases you can associate to locally free sheaves of vector fields a de Rham complex. Well, so this is the abstract theory, but now let me try to tell you what this theory looks like locally. What actually are these B vector fields? What are these B de Rham forms? Well, to answer that question, we have to understand this B vector bundle that I've just defined. And so what is this B vector bundle? Well, it's easy to see. The following is pretty obvious, that if you have an open set that doesn't intersect this hypersurface Z, then the B vector fields on that open set are just the usual vector fields. So that means that any point not on this open set that doesn't intersect B, the tangent space to P, the B tangent space at P to M is just the same as the ordinary tangent space at P to M. So the only interesting thing happens when you're at a point on Z. And so now what does this B tangent space look like at a point of Z? Well, so one thing that you have is that you have a natural restriction map. If you have a vector field on U which is everywhere tangent to Z, then it restricts to give you a vector field on Z. So so you have a natural map from the sheaf to this intersection here. And interpreted in terms of this vector bundle, this gives you a map from the B tangent space at P to M to the usual tangent space to Z. And it's easy to see that this is a surjective map. But this is a vector bundle with fiber dimension M, and this is a vector bundle with fiber dimension N. So there has to be a kernel to this map. And what is the kernel? Well, let's fix a function on R, on M, a real valued function that is a defining function for Z. So it vanishes on Z and vanishes nowhere else, and is a defining function for Z. So fix such a function. So then you can define a kind of a screwy vector field. You do this. You take W to be a vector field on M, any vector field on M. Then, of course, if you multiply it by F, it's obviously a section of this B tangent bundle because it is not only tangent to Z, but it vanishes along Z. And so that means if we evaluate this should be sort of in parentheses here, at a point P, we get an element of the B tangent bundle at P. And actually, it turns out that if we normalize this vector field W so that dFP of WP is equal to 1, this element is an intrinsically defined element of the tangent space at P. You change the data, you get the same basic B vector field at P. So that's a nice fact that this B tangent bundle at P has an intrinsically defined element, this vector field V. And then from this, you get a very nice little diagram. Namely, at any point over Z, you have a very nice exact sequence where here you have the B tangent bundle restricted to Z. Here you have the usual tangent bundle of Z. And then the kernel is a trivial line bundle, which has, as its fiber at each point, just constant multiples of this completely intrinsically defined vector field that I just defined. Well, and then you have a dual picture that goes along with this. Namely, if you have an element in the cotangent space, the B cotangent space at B, and you pair it with this completely intrinsic vector at P, and the pairing is equal to 1, that means that this element U at P is sort of, in quotation marks, dF at P over F of P. Of course, in real life means absolutely nothing because f at p is equal to 0. But unless you have an object which is symbolically this quotient, and it's well-defined modulo honest elements of the cotangent space at p. So this is sort of the dual picture to this vector field is this weird-looking object called df over f. So the upshot of this is you have a well-defined B1 form, which at each point p is this df of p over f of p. And then it's easy to see that every B de form can be written as a wedge product like this. It's a wedge product of this weird object df over f wedged with an ordinary de form, and then you add to it another ordinary de form. So this is what B de forms look like. Okay, and then the upshot of this is that, so this is what B de forms look like these objects on my previous slide. Every B de form can be written as a wedge product with ordinary de forms, and then you have to insert this df over f guy. So this is B de theory. Now the next question I want to ask is, in B de theory, what are closed de forms? What do they look like? So let me prove for you the following proposition. Take a tubular neighborhood of this hypersurface Z, and then a B de form is closed on this tubular neighborhood if you can write it as a sum like this, omega equals df f wedge mu plus nu, where the mu and nu are both closed de forms. Let me sketch a proof of it since it's very easy to prove and it's going to be a basic result in this talk. So here's the proof. So by my previous observation, you can write omega as the ff wedge sum de form plus sum de form. And moreover, if d omega equals 0, what does that mean? Well, you apply d to that. That's 0. That's df df, and then d applied to that plus d applied to that. So, so this means that dff wedge that is equal to minus, d of that is minus d of that. And if you multiply that then by f, this then tells you that df at p wedged with d of this form mu tilde at p has got to be equal to 0. So this is equivalent to saying that the restriction of this form mu tilde to z has got to be closed. D of it has got to be equal to 0. And now take this projection of mu onto z, like that, and pull this form back. This guy is then a closed form. And then you can do the following. This then tells you that this form minus the form you started with, restricted to z, is equal to 0. So for any p in z, d mu minus d mu tilde is df of p wedged with some element of the exterior algebra of degree k minus 2. So this means that this form minus this form vanishes on z, and that means that df wedged minus this guy is perfectly well-defined C infinity de form on U. And now you just take omega minus dfu and replace nu tilde by this guy here. Then you're done. Both of the forms in that expression are now closed forms. Well, this has some nice consequences. The first consequence is the Poincaré lemma. It says that if omega is a B de form, very important here is that k be greater than 1, and I'll explain why in a second. Then for every p in z, there exists a neighborhood on which this form omega is exact. And the proof, well, you have this decomposition of, well, let me lose it here. Yeah. You had this composition of omega into this wedge product involving forms mu and nu. And now you just apply the usual Poincare lemma to these mu and nu. These are closed forms, and so that means that on some open set they're exact. That is the Poincare lemma. Another very nice result that comes out of this is the so-called Mazzeo-Melrose theorem, which says that the B de Rham cohomology of this manifold M is actually isomorphic to the usual de Rham cohomology in dimension K, to the usual de Rham cohomology of N plus, and then the K minus 1 de Rham cohomology of the surface Z, hypersurface Z. You have this very nice description of B de Rham cohomology in terms of ordinary de Rham cohomology. And from this lemma I just proved, the proof is relatively easy. You have this expression of a de Rham form as df wedge mu plus omega, and if this is closed, this mu is closed. And now you look at this restriction map where you take this closed form, restrict it to Z, and that introduces a very nice map from the B de Rham cohomology of M into the ordinary cohomology of Z in dimension K minus 1. And then it's very easy to check that the kernel of that map is exactly the usual de Rham theory of M in dimension K. Well, but as I pointed out a second ago, this Poincare lemma that I described doesn't work in dimension K equals 1. And there's a very good example for why it doesn't work in dimension K equals 1. Namely, you have one wonderful closed example in this theory of a closed one form which is not exact even locally. And so to remedy this defect, we do the following. We want to have a Poincare theory that works in all dimensions. And so and so the way you do this is you first of all try to find the relevant slide for this. Yeah. Well, I can explain, maybe on the blackboard. If you give me a second, I can maybe locate this a bit. Excuse me, what? You're right. This is a slide I was looking for. So the way that you remedy this is a sort of a nice, obvious way of doing it, which is you introduce into the world of functions a new class of functions which you call B functions. There's a... There should be absolute value here, sorry. So what you do is you take, for each connected component of your B hypersurface, a defining function for that connected component, a function fi which vanishes along that connected component and is non-zero everywhere else. And then you add to your collection of ordinary B forms these guys. And these guys have the property that if you take d of log absolute fi, you get dfi over fi. So any form of, any expression of the form df over f, or more generally dfi over fi, is now going to be d. So by adding these functions to your repertoire of C infinity functions, you've now ensured that the Poincare lemma is true even in dimension 1.
Are you not allowing to multiply
You can multiply these things to your heart's content. CI constant is okay. Well, no, I'm not sure. At any rate, this introduction of these functions remedies this problem locally.
If you have one of these functions and multiply it by smooth functions, that's still allowed? If your f over f you multiply it by smooth function, not by constant, do you allow that?
No, we don't allow this. No, we don't allow this.
So what you've introduced does depend on your choice of defining.
Yes, very definitely, yeah. Okay, so now let me pass to the second half of this talk. B-symplectic forms. So now, from now on, I want to assume that my manifold is 2n dimension, and I give myself a B form, and I call it I call it in dimension 2, and I say that it's symplectic if it's closed and satisfies the certain standard symplecticity requirement, that is, wedge product with itself n times is nowhere vanishing, but as an element of this kth exterior power of the B cotangent bundle. So this then is the notion of a symplectic form. Well, what do such forms look like locally? There is a sort of a local Darboux theorem that, sorry, there's having issues here. There's a local Darboux theorem. Wait a minute, I'm still, Jesus. I'm sorry, people, I've kind of gotten all my, I know what's happening. I had a pile here and a pile here. Okay, so the first version of the Darboux theorem that I want to run by you is this. It's the theorem that I just proved. It says that this form omega can be written in a neighborhood of z as dff wedged with alpha plus nu, where alpha and nu are both closed, ordinary closed de Rham forms. That's the theorem I just proved in general, and now I apply it to this b-symplectic form omega, and I have that theorem is true for omega. So this is sort of a semi-global Darboux theorem, and then there is a local Darboux theorem, which is an easy corollary of this, and it is exactly the Darboux theorem that you might suspect, that there exists in the neighborhood of every point a symplectic, a system of symplectic coordinates, a Darboux coordinate system, so that my B form on that neighborhood looks like the usual Darboux B form, dx1, dy1, dx2, dy2, and so on, except that the B hypersurface is defined by x1 equals 0, and instead of having a dx1 here, I have a dx1 over x1. So that's what Darboux theorems look like in this B theory. And so finally, before I finish this segment of today's lecture, I would like to, since this conference is a conference in Poisson geometry, say a little bit of what b-symplectic manifolds look like from the point of view of Poisson geometry. So I want to, so in Poisson geometry, these have been around a lot longer than in b-symplectic geometry. So the definition is the following. Let's suppose we have a Poisson manifold where pi is the Poisson B vector field. So definition, we'll say that M is provisionally B Poisson if the following map, you take P at M and map onto the nth wedge product of this guy, if this map is transverse to the 0 section inside of the 2n cotangent wedge product of the tangent bundle of M. Sort of a natural transversality, very natural transversality assumption. And so if this is the case, then it turns out that this set where the B-Poisson vector field vanishes is a codimension 1 submanifold of M. And then the definition is that M is B-Poisson if the symplectic leaves of the Poisson structure at points of Z are actually codimension 1 submanifolds of Z. So that you add that little additional requirement and you've got B-Poisson. Now, what is the relationship between B-Poisson and b-symplectic? Well, let's go to our canonical form for the symplectic form in a neighborhood of Z, df alpha plus nu. Then the symplectic form and b-symplectic form and b-Poisson form are compatible descriptions of the same B object if the following is true. For P not in Z, omega P and the second exterior power of the cotangent space is just the dual object to pi at P in the second exterior power of the tangent space. And the other assumption is this, that if you take this form alpha and restrict it to Z, it's the defining one form for the symplectic foliation on M. The symplectic foliation on M, locally this form alpha is going to be D of something, and the foliation, D of H, let's say, height function, and this foliation is defined by this height function is equal to constant. So the alpha defines the symplectic foliation, and for any symplectic leaf on Z, the restriction of nu to the leaf is the symplectic form on the leaf. So very, very clean connection between the theory of B-symplectic forms and the theory of B-Poisson structures. Okay, so this finishes essentially this segment of the talk, and then the third segment of the talk is sort of going to, it depends on how long it lasts, but it might be a joint talk with me and Jeff, but okay, at any rate. I'll try to go very fast. You were urging me to go very slow. If I go fast enough, then Jeff will add the finishing touches, but maybe I'll get kind of stranded midway. You're approving of. Okay, so G actions. So let G be a compact connected Lie group, strip G its Lie algebra, and gamma an action of G on M. And I'm assuming that this action preserves the B-symplectic form. So it preserves Z and it preserves the B-symplectic form. We'll say that this is a Hamiltonian action if there exists a B moment map. So it's a map from phi not into the ordinary functions, but the B functions tensored with G star. And it's a G invariant map, satisfying that for every vector in the Lie algebra, you have this identity. The corresponding vector field on M, inner product omega, is O. Is D of this function phi composed with phi. So the usual moment map condition, but the only difference here is that this moment map is taking its values in B functions, not in functions. So it's from the usual C infinity world, a kind of a singular object. Okay, so what I want to do in this last segment of the talk, discuss a result that Eva and Jeff and I, and together with Rita, Pires, proved a sort of a B version of the standard Delzant theorem in ordinary. So for this to make sense, we now have to assume that our group G is a torus, and that the action of G on M is a toric action. That is that G is an n torus, and the dimension of M is 2n, and that this action is a faithful action, is an effective action. Now let's go back to these defining functions, Fi, for the various connected components of the B hypersurface Z. then we can do the following. So the moment map that I wrote a second ago can now be written in terms of these b functions as follows. Phi equals log fi tensor nu I plus a remainder term, which is a purely C infinity object. And these nu i's are elements of the Lie algebra, the dual of the Lie algebra. And they play an incredibly important role in b-symplectic, equivariant b-symplectic geometry. They were invented by Alan Weinstein. Well, I mean, they're closely related to something that Alan invented, I think in the mid-90s, modular geometry. And they are called the modular weights of this b action. And they're very, very closely related to an object that Alan invented called the modular vector field. So you have these modular weights, which are sort of God-given elements of the dual of the Lie algebra. And our first main theorem in the subject is that in the setting that I've just described, there exists an element nu. Actually, it lives in the weight lattice of G. At any rate, it's an element in G star minus 0, such that all these modular weights are non-zero multiples of this element nu. So all the modular weights line up with each other. They're multiple, constant multiples of each other. And a very important corollary of this is that if you let K be the subtorus of G, having as its Lie algebra all the vectors that annihilate this nu, so these are going to annihilate all the modular weights, then the action of K on M is a standard Hamiltonian action. No singularities whatever, with a standard C infinity moment map. Claim and the proof, well, the proof, I apparently didn't write it here because it's so completely obvious. The way the proof works is you go back to this formula for phi. Now, if V is a vector in the Lie algebra of G, which annihilates the nu i's, then this phi evaluated on that vector is going to be completely C infinity. This whole term is going to vanish. So that's what guarantees that this subgroup actually has a standard Hamiltonian action. And there's some other very nice properties of the action of the group G restricted to this subgroup K. I think I can make it. One property is that let's take, we have this symplectic foliation on Z. And the first assertion is that if X is a symplectic leaf of Z, then the action of K, which obviously has to preserve Z, actually preserves this symplectic leaf. The K action on Z preserves all the symplectic leaves. And the proof of this, well, here's the proof of it. We take V in K, and we take its interior product with omega, and it's going to be an expression like this, dFi over Fi, and then the interior product with this alpha I. And that means, of course, if this is a C infinity function, that this interior product has got to be 0. But remember, this alpha is the one form that defines the symplectic foliation on Z. So that tells you that this vector field has to preserve the symplectic foliation. So the action of this subgroup, codimension 1 subgroup of G, on the manifold M preserves the symplectic foliation. And a corollary of this is that the action of K on M restricts to a standard Delzant action of K on X for every symplectic leaf. Because The symplectic leaves are 2n minus 2 dimensional. K is an effective action, symplectic action, of an n minus 1 dimensional torus on each of those symplectic leaves. Okay, so now let me come to the second main theorem that we were able to prove, which is this, that for every pair of symplectic leaves, the Delzant actions on these two symplectic leaves are identical. Same action, isomorphic. Well, this is very, very easy to prove if the two symplectic leaves are on the same connected component, thanks to this wonderful invention of Allen's called the modular vector field, which in this case, Allen, is just a circle action, taking each leaf to every leaf to so this modular geometry permeates this whole subject. So one very important symplectic invariant means that we now have associated to our symplectic manifold an intrinsically defined Delzant manifold. Take any one of these symplectic leaves, take the K action on that leaf, you get a completely intrinsic Delzant manifold with a completely intrinsic Delzant polytope. Another important symplectic invariant attached to this picture is the following. So we have this moment map associated with the K action, and this is a standard Hamiltonian moment map. There are no B elements in its definition. Well, take a regular value of this moment map and symplectically reduce. So we take phi inverse of alpha and take the symplectic reduction with respect to the K action. Well, this is, of course, a two-dimensional manifold. It's not a symplectic manifold, unfortunately. It's a b-symplectic manifold. It still has a bad B moment map. But it is a symplectic B manifold and is equipped with a B action of the circle group G over K. You have a residual action of G over K on this manifold. Well, what does this mean? You have a two-dimensional manifold and you have a circle action on it. So what does that mean? Well, it means that this two-dimensional manifold associated with this value alpha is either a copy of S2 with its standard circle action, rotation about the z-axis, or it's a copy of T2 with a standard rotation action S1 cross S1 gets rotated by the S1 on the second factor. It's got to be one of those two guys. And we will call the two alternatives that this presents the two-sphere case and the two-torus case. So you have for every one of these toric B manifolds, you have as its first invariant this Delzant manifold, and as a second invariant, you get a two-dimensional circle action, a B Hamiltonian circle action on a two-dimensional manifold, which is either going to be S2 or is going to be T2. So let me tell you what happens in the two-torus case, because that's kind of the simplest story. So in the two-torus case, we have theorem. These M alphas, these two-dimensional manifolds, are all isomorphic. They're the same for all alpha. And they are isomorphic as B Hamiltonian manifolds to a fixed T2 with a fixed Hamiltonian B structure. So what you pick up in this B theory is an honest Delzant manifold of dimension 2n minus 2 and a completely God-given B manifold of dimension 2. And the main theorem is this. Theorem. The manifold M that we started with is the product of this Delzant manifold, product with this T2, the action of G on M being the product of the action of K on the first factor and the action of S1 on the second factor. That's our classification theorem. Now, the situation in the S2 case is a bit more complicated. So roughly speaking, it says the following. So you have this S1 action on the two-sphere. Think of it as rotation about the z-axis. And so it leaves invariant the north pole and the south pole. And now what you can do is, in the vicinity of these 2 points, so you first of all start out by taking this product of M with x cross S2. And then you have on this space these polar caps, points close to 0, 0, plus 1 cross x, and then 0, 0, minus 1. And then you do a certain number of, a bit of surgery. You do symplectic cuts on these polar caps, making sure that all the symplectic cuts are completely away from the hypersurface Z. You're just doing little amputations up on those polar caps. And that gives you everything. And this, so Jeff. So what I left out of this picture is a very important object that I didn't think I would have time enough to describe. Namely, in the ordinary Delzant theorem, what Delzant tells you is that the Delzant manifold that you stare at is completely determined by its moment polytope. That's Delzant. That you get the moment polytope is the image of the moment map, and that completely determines the Delzant manifold. Now, you haven't seen in my talk any mention of a moment polytope, but it exists.
So first I wanted to apologize to all of you. I learned that I was coming up here the same time you did, so this might sound a bit like math trivia.
Oh yeah, can we get to, yeah, just a second. This goes up.
Yeah. And I also want to mention, if you were at the mini courses, if you listened to Marco's wonderful mini course last week, he called these objects
turn this off.
Log manifolds and log symplectic manifolds. And b-symplectic and log symplectic are 2 names for the same thing. So if you thought this, I'm familiar. Okay, so the question that Victor posed, and I hope to...
Jeff, do you have a microphone?
I don't. Should I?
Yeah.
So the question that Victor posed, and that I hope to answer in about 7 minutes or so, is there a Delzant picture for these b-symplectic manifolds? Is there a way to construct a moment map so that the image is some kind of convex object which captures the geometry of these b-symplectic toric actions? And of course, I'm not going to have time to go to all the details, but I want to draw some pictures for you. So the naive approach that you might take to constructing these b-Delzant polytopes, whatever they are, is to start with the simplest example of a b-symplectic manifold you can imagine with a b-Hamiltonian torus action, namely the sphere, with this b-symplectic form where the singularity is along the equator, and you might take a look at the action given by del theta. And if you naively go through Hamilton's equations, you'll learn that this action is generated by the b-symplectic, the b function log absolute value of h, or it's negative depending upon your conventions. And if you graph the image of this function, well, the north pole goes to 0. And as you go further down, I guess this goes to negative infinity. And along the equator, it hits negative infinity. And then as you go to the south pole, it goes back up towards 0 again. And so this isn't a very good moment map because, first of all, the orbit corresponding to the equator isn't represented anywhere in the image of the moment map. And the second issue is, even if we were to say, OK, let's add a point down here at negative infinity, and that solves this problem, even if we do that, this moment map would not be injective on the space of orbits. And one of the really nice properties of classic moment maps is their parameter spaces for the orbits of the torus action. So we would like our new moment maps to have this property as well. So the solution, and I'm going to draw the picture and then write the equations later, is to define a new codomain for these moment maps. And what it's going to be in this case is we're going to take two copies of the real line. Here's one and here's the other. And I'm drawing them kind of curved because we're going to compactify these two copies of the real line by adding a point at negative infinity. And the new moment map that we're going to get will send this north pole to the copy of 0 on this branch of the this branch that's isomorphic to R. And as we go from the north pole to the south pole, we're going to travel down here. We're going to hit the point at negative infinity, and we're going to travel back up to the 0 over there. So this will solve our discomfort of this moment map. OK. So let me write just a few equations of how this happens. First of all, given a b-symplectic toric manifold, we're going to define what's called the weighted adjacency graph, which I'm going to call script G. And it's going to be a graph together with a weights on the edges. So this graph is going to have a vertex for each component of the symplectic manifold minus the critical hypersurface, minus Z. So I'm going to call this the adjacency graph. And this W, so the vertices correspond to connected components of M minus Z, and the edges correspond to the components of Z. And W is going to be a function from the edges of this graph. Remember, those correspond to the components of Z, and it's going to send it to T star. So an edge gets sent to the modular weight corresponding to the corresponding component of the critical hypersurface. And given one of these weighted adjacency graphs, well, the first comment I should make is we prove in our paper that any such weighted adjacency graph corresponding to a b-symplectic toric manifold will be either a line or it'll be a cycle. So the adjacency graph is very simple. And moreover, the image of this weight function, all the points will lie on a certain line in T star. Okay?
So T star is G star, lowercase b star.
Yes.
This is this theorem that all the modular weights are multiplied.
Yeah, all the modular weights are multiples of each other. So give me 5 minutes, and then I can finish up this construction. So given one of those, we construct the B moment codomain RG, ZG, and X hat. And I'm not going to tell you the construction. I'm just going to tell you the salient properties of this space. First of all, RG, ZG is a B manifold. In this picture here, this entire space is RG, ZG, and ZG is going to be these points at infinity. And this X hat is going to prescribe the affine structure on each of these spaces. So X hat is going to be a map from RG minus ZG to the dual of the Lie algebra. And each component, so it's going to be an isomorphism on each component of RG mod ZG. So really keep this picture in mind as I'm going through these properties. So each component of ZG will be isomorphic to TZ dual, where this TZ is the codimension 1 subspace of the Lie algebra, which is perpendicular to this one-dimensional subspace of the dual of the Lie algebra given to us by the image of these weights. And finally, I won't write this because I don't have space and I don't have time, but the smooth structure on this B manifold will be prescribed by these weights. And the kind of the raison d'etre of these b-moment codomains is smooth maps to these b-moment codomains correspond precisely to b functions with the modular weights given by this. So this is why using the tools of b functions is kind of a powerful tool to use when studying these group actions on b-symplectic manifolds. Okay, so given one of these spaces, one of these b-moment codomains, there's a notion of a Delzant polytope on one of these b-moment codomains, which corresponds with the notion of Delzant polytopes on this subset of the b-moment codomain that's isomorphic to T star. I'm not going to write this down. And the theorem, which is a generalization of the Delzant theorem, so this is okay, is there's a bijection between the set of all b-symplectic toric manifolds. So this is going to be a quadruple, m, z, omega, and a map from m to one of these b-moment codomains, and polytopes, Delzant polytopes in these b-moment codomains, and where, of course, this set should be understood as up to equivariant b-symplectomorphism preserving the moment map, and that set should be understood up to the appropriate transformations in these spaces, which I'm not defining. And so that's the generalization of the Delzant theorem. And let me just say one or two other things, is that very recently there's a paper of Gualtieri, Palaio-Vertu, and Lee, which kind of does another version of this B-Delzant theorem, but uses a different object as a codomain. And I think we're going to hear about that tomorrow, which I'm excited about. And also, you might wonder whether we can get convexity for TK actions on b-symplectic manifolds when it's not necessarily toric. And the answer, which we recently found, is yes. So I just wanted to advertise that a little bit. So let's thank Victor for his very nice talk.